Recording. Hey, everybody. So in this set of notes, we are going to be talking about differential equations. What is a differential equation, you might ask? Well, it's an equation that involves an unknown function, which is the function that we want to solve for. And we'll call that unknown function y. It could be any function. You could label it however you want. We're just going to call it y. And because it is a differential equation or derivative equation, it also needs to involve one or more of y's derivatives. And like I had just mentioned, the solution to a differential equation is actually solving for that unknown function. Okay. So what I want to do now is show you some examples of differential equations and their general solutions. Because keep in mind, when we take the derivative of whatever we find as our general solution, it doesn't really matter what that constant is because it'll end up going away. So that's why there are actually general solutions to these differential equations. You can find a particular one if you know some specific information about it, but general solutions are okay for these. So let's say that I wanted to solve the differential equation y prime equals negative 2y. The solution to that differential equation is actually y equals c e the negative 2x. And the way that you could verify this is by taking that y equation and plugging that in for this y, and then taking the derivative of that y equation and plugging it in for the y prime, and making sure that you get a true statement at the end. And if you don't like the idea of checking that with a general c in there, you could always do a specific constant there and just check. All right, next one, let's say that we have dy dt. Let me try to get this smaller. So dy dt equals, let's go with t. The general solution for that specific differential equation would be y equals 0.5 t squared plus c. And again, you could check that the same way. T is just a regular t. Take the derivative of this, and you should actually get, yeah, what's the derivative of that? T. So when you plug in the derivative of that equation, you get t equals t, which is true. All right, let's go with just one more example. So here's a differential equation, y double prime plus y equals 0. The general solution for that differential equation is y equals, and this general solution actually has two constants of, we'll just call them constants. So I'm actually not going to use c. I'll use a and b. It really doesn't matter. They're just general constants. So it's a sine of x plus b cosine of x. If you were to take the second derivative of that, put it here, add this exact equation to it, everything would cancel out and you'd get 0. And if you're curious, why not do that right now? You can pause the video and try it out. I'm not requiring you to do that though. Okay, so let's move on to example 1. Verify that the function is a solution to the differential equation. So that's what I was saying the entire time. Are you convinced that these are actually the general solutions to those differential equations? Well, take all of the information that you know, plug it into that differential equation, and make sure that you get a true statement. Now, when you actually do this in practice, it might seem really silly to like show all of your work, but simplify one step at a time. I know you might be able to just plug things in and then see immediately, oh, this is going to work out. But humor me, simplify one step at a time before you go straight to saying, oh, this works. So what I'm going to do here, because I like to just plug my expressions into my differential equation, is I'm first going to find the derivative of this y equation, which means, because I do actually have a composition of functions, rewriting this in powered form first. So it makes it easier for me to actually differentiate. Okay. So the derivative of this, let's see, the outside function is the power of 1/2 function. So it's 1/2 parentheses to the -1/2. And then I'll go ahead and put that inside function back in. All right, and then I'll multiply by the derivative of that inside function, which is -8x. I am going to go ahead and simplify this. I noticed that I have a -8x and a 1/2 that I could multiply together. I can't really multiply anything within the parentheses because it is to an exponent and there's multiple terms inside of it. So I can't really do anything with that. But when I multiply those two, I get -4x. And what I'm also going to do is, because that power is negative, I'll put that entire expression in the denominator. Don't worry, guys, I got this. And if you want, you could also write that as -4x over the square root of that expression. Okay, so what I'm going to do now is verify that this y equation is actually a solution to that differential equation. And I'm going to do that by plugging in all the information that I can and simplifying and hopefully getting a true statement. So give me 1 second, we'll get that going. Okay, so plugging in the y equation, that was the square root of 12 minus 4x squared. And what we got for y prime was -4x over the square root of 12 minus 4x squared. Plus 4x, there's nothing to plug in for that. It's literally just 4x equals 0. I'm putting a question mark because I am not 100% certain yet. I mean, personally looking at that, I am very certain, but I haven't actually fully verified. So let's go ahead and start simplifying. Remember, one at a time, please. So I'm going to go ahead and cancel out the square roots. So I'm left with -4x plus 4x equals 0. Those also reduce to be 0 equals 0. We have verified that that equation that we had for y was actually a solution to that differential equation. All right, now I would like to show you guys how you could actually find those unknown functions, how you can solve for them versus just verifying that somebody else found the correct answer. So the way that we're going to do that is first by rewriting whatever the derivative function is in Leibniz notation. Remember, if it's y prime, you'd write dy dx, or dy d whatever independent variable you have is. Now, if we have y double prime anywhere, that would be d squared y over dx squared. Now, I'm not necessarily saying that correctly. That's literally just we're taking the second derivative with respect to x twice. You can leave that on your notes if you want, maybe next to step 1. Then what we do is we're going to separate the variables so that the y terms and the y's are on one side, and then the x terms, and if any constants can go over there, you can. It just depends on how things move nicely. However, we will be integrating. So the dy needs to be in the numerator. So does the dx. That way they are actually in the correct differential location. We don't put those in the denominators. That's just not correct notation. Sometimes you might need to add or subtract things to the other side. Sometimes you might need to divide them. Just make sure that everything lines up nicely. Once you are ready to integrate, we need to keep it general. However, you don't need to put plus c on both sides. That's going to look weird, and then you're going to think that it's going to cancel out. So just use plus c on the side with the independent variable, which is where we're going to want it in the end anyway. We just need one to be able to keep everything general anyway. And then solve for y. Okay, so looking at this example here, is this actually the one that you have? Let me go double check really quick. I might need to fix that. No, that was not it. I needed to put this new equation up there. That's all right. So getting started here, we already have the derivative rewritten in Leibniz notation. The derivative is the dx dt. So if we had to rewrite that, it would have originally been x prime equals, or x prime minus 5x equals 5. And if we're looking at just that, we don't really see an independent variable, because since I see that x prime, that tells me that x is my dependent variable, like y usually is. So if this was the original equation, we could choose our own independent variable. And I think t is a very nice one here versus if I chose y, because that just seems so backwards compared to what we're used to that you might have gotten confused. So what I want to do from here is go ahead and add that 5x to the other side. And the reason why I want to do that is because I want to be able to separate the dx and the dt. And if I try multiplying that dt to the other side, I would have dx minus 5x dt equals 5 dt, and I would have too many of them. I don't want to have more than one dt. I only need to integrate with respect to dt, or with respect to t once. It would be too many if I had them like this. And what happens with me adding that 5x to the other side is that now I can treat that right side as an entire factor. And I don't necessarily have to distribute that dt to both of those expressions. Okay, so I am going to actually move that dt to the right side. That way I have a dx in the numerator and a dt in the numerator. And I'm also going to divide the 5 plus 5x to the left side. That way I have all of my x's on one side and all of my t's on the other. Okay, and we are ready to integrate. This is definitely an expression that I can integrate. I will have to do a small u substitution, but if you feel skilled enough, you don't have to. And on the right side, I just have a dt, or if you want to write that as a 1 dt, if that makes integrating that easier, go for it. So the reason that I'm going to do a u substitution on the left side is because I do have more than one term in the denominator and we don't have a quotient rule. But the reason the reason that I said you don't necessarily need to do a u substitution for this is because it's just a linear expression in the denominator. And there's a unique thing that happens whenever your inside function, or because I mean, technically this is an inside function. You have some expression. Well, I'll show you in a second. Well, yeah, no, I can write it like that. You have some expression raised to the first power, or I could rewrite that as that expression to the negative first power. So we do have an inside function that's just linear. And when you do u substitution, the same thing happens every single time. And I'll show you that. Solve for dx. Oh, I'm sorry, the derivative is just 5. There we go. Right, so I'm gonna go ahead and replace that. 1 over u times, well, technically that's du over 5. So what does happen every single time that you do a u substitution with the linear expression is the derivative of that linear expression is literally just going to be the coefficient on that x value. And every single time you'll get du over the coefficient. That's it. So I could have seen when I integrated this immediately, the final result. It would have just been whatever I knew that the derivative of 1 over the expression is times 1 over the derivative of that inside function. Okay, so I'm going to integrate this anyway. The antiderivative of 1 over u is ln absolute value of u, and then I'll multiply by that coefficient of 1/5. This is the side where my dependent variable was, so I'm not going to do the plus c here, but I will do it on the independent variable side. Antiderivative of 1 is t, keep it general. Now there's a few things that I want you to remember as we go about solving for, well, after I replace this x in our equation. C is just some arbitrary constant. So if you end up having to multiply it by some number or divide it by some number, it is still just some random number, C. So we're not going to necessarily multiply it by anything or divide it by anything. All right, so I am actually going to, I'll wait to multiply by 5. I'll go ahead and replace the u with the 5 plus 5x really quick. Now I'm going to go ahead and multiply both sides by 5. We get 5t, and then I will write plus 5c for now, but write yourself a note that 5c is still some arbitrary constant. So just write it as c. So I'll take care of that in the next line. What I want to do now is figure out how to undo that natural log. Anyone remember? the inverse to a natural log is e. So if I take e and then raise both sides into e's exponent, and remember I'm writing that plus 5c is just a regular plus c. The e and the natural log cancel out, and I'm just left with the absolute value of 5 plus 5x equals, and remember your exponent rules. What was the original scenario that made it so that I could add those exponents? Multiply the same base, you add the exponents. So if I just rewrite that as e to the t times e to the c, I would go ahead and get back to that spot where I have those exponents being added together because I am multiplying the same base. Now, e to the c, hopefully you know what I'm going to say right now. It's still just some arbitrary constant. So I'm just going to write c. And I'll write it in front of the e to the 5t. At the same time, I'm also going to get rid of those absolute value bars, which remember when you're solving absolute value equations, you write plus or minus on that other side. Remember, rewriting that e to the c is just a c, some regular constant, some arbitrary constant. And again, the same thing is happening here. C is still just some arbitrary constant. I don't care if it's positive or negative, just write C. All right, and then we can go through the process of solving for x. Subtract 5 to the other side. Again, I'll write regular C instead of plus or minus. And then I'll divide by 5. And I am going to divide each individual term by 5. But C over 5, still some arbitrary constant. Just write it as C. So our final answer is x equals C e to the 5t minus 1. And now we also know how to check it, which I'm going to get the calculator out and show you guys how to quickly check it on there versus doing what we did on the first page in example 1. So what I'm going to start off with doing is writing the x equation in my graphing calculator. I'll just pretend it's a y though. So just pretend this is y equals c e to the 5x minus 1. And I can't just put c in there, so maybe I'm going to pick some random number. And I'm not going to use 5 because I don't want to be confused with all the other 5s that I have. So maybe I'll just put a 9. So 9e to the 5x minus 1. And this isn't what I'm graphing. So I'll turn that off. What I want to check is that when I plug the x into this part of the equation, I get 5 as a result every time. So I should end up getting 5 as the output for every single one of the values that gets plugged into this. So it should end up being a horizontal line of like y equals 5. So we'll do y equals y1 prime. Oh, actually, I want to do the derivative of that. So n deriv. Oh, yeah. y1 prime minus 5x. I should end up getting 5 as a result for every single one of those. No, did I type that in wrong? Let me double check here. I see what I did wrong. I should have written this down. So because I replaced the x's with y's, this is technically like dy dx or y prime minus 5y equals 5. So I replaced all of the x's with y's. So technically that should be minus 5 y1. Maybe it would have just been easier to verify this by hand. All right, now we should get all outputs of 5. Yes, and sometimes it freaks out a little bit in certain areas, but that is still 5. Keep in mind your calculator is doing high level approximations, whereas we're doing some nice, quick, easy math. And I could always look at the graph too. Yeah, so it looks like this function kind of breaks close to 2. Next thing I want to talk about is finding a particular solution when an initial condition is given. So we will solve this in general with that plus c at the end, but then we'll plug that initial condition in so that we can solve for c. So starting this off like last time, we want to replace any derivatives with the Leibniz notation. So I am going to go ahead and rewrite this as t cubed. And then instead of y prime, that'll be dy dt, considering that the independent variables that we see here are t. Make sure that you put 1 plus t squared. Every single time that I've done this on paper, I accidentally write minus. All right, so let's go ahead and rearrange this so that the y's are on one side and the t's are on the other. I am going to move the y's to the left side because I have a dy over there and I want the dy to be in the numerator, and then I'll move the dt to the right side and all of the other t's over there. So moving that, I'd multiply that y right here to the left side. And then I'll multiply the dt to the right side, divide the t cubed. And now all of our variables are separated. We can go ahead and integrate. So the integral for the left side would be y to the power of 2 and then multiply by the reciprocal power. Remember, we don't put plus c on this side. We'll put the plus c on the side with the independent variable. Now for that right side, I can't really integrate it with the form that it's in. We don't have a quotient rule for integration. However, I could just divide those individual terms in the numerator by t cubed, and then I would get a nice polynomial-esque equation. So 1 divided by t cubed, that would be t to the negative 3. And then t squared divided by t cubed, that would be 1 over t, or I could write t to the negative 1. Whatever your preference is. Put parentheses around that entire expression and then the differential. And now we are good to integrate here. All right, add 1 to the power, divide by that power. Antiderivative of t to the negative 1 is ln absolute value of t. Keep it general. Okay, so now we are going to go ahead and solve for y. Multiply both sides by 2. And that 2 is going to get distributed to every single term on the right side. Remember what we talked about in the last problem though, that 2c, that is still just some arbitrary constant. So instead of writing 2c in the next line, I'll just write that as a plain old c. So again, I'll do that in the next line. But what I want to do for now is square root both sides to get rid of the square. And remember, when you are solving by square rooting, you need that plus or minus. And I'm just simplifying the right side as I go. Again, instead of plus 2c, I'll just put plus c. So this would be our general solution. Yes, that plus or minus needs to say in front. When you end up solving for a particular solution, it'll be very clear whether or not you need the plus or if you need the minus for any particular solution that you might have. So I'm going to go ahead and write my initial condition off to the side and then write the general solution down underneath it. So our initial condition is y of 1 equals -5. So keep in mind here, 1 gets plugged into the expression, -5 is the output. So -5, and then I'll write the general solution down. Oh, those t's should actually be 1s. Okay. So this is where I need to decide if I need the plus or if I need the minus for that square root. Because I'm getting an output of -5, the only way that that will ever happen is if I use the negative from the plus or minus. So we're going to get rid of that plus. And then I'll simplify the inside. So -1 over 1 is still -1. Plus 2, natural log of 1 is 0. Divide both sides by -1, we get +5 equals positive square root of, let's see, just -1 plus c. Square both sides, you get 25 equals -1 plus c, which means that c equals 26. And we can go ahead and write our particular solution up. And just like last time, we can check that because you might be feeling pretty, is unconfident a word? Might be feeling a little unconfident about whether or not that's the correct answer. So you could do the same way that we did example 1. You could verify that this is one of the correct particular solutions by plugging it into your differential equation. Or again, I'm going to show you how you can do it on the calculator. So I'm going to just go ahead and type the equation in for the particular solution into y1. Negative square root -1 over x squared instead of t plus 2 ln, let's do absolute value, of x and then plus 26 after the parentheses. You don't want to accidentally put that inside of the natural log. All right. So then in the second line, I'll type in the left side of the differential equation. In the right side, I'll type in the right side of the differential equation, and they should overlap. They should be the exact same graph if everything was correct. Okay. So I'll put x cubed instead of t cubed, and then y1 prime equals 1 over 1 plus x squared over, instead of y, we'll do y1. Times the derivative of y1, so math 8. we have an x equals x. That way it's actually graphing the function. And then in line 3, so long as the solution is actually correct, we should get the same output expression from both the left side and the right side. Oh, x squared. Yep. Divided by y1. All right, so I'll turn off the y1 function, and then we'll see if the left side of the differential equation equals the right side of the differential equation with this particular solution. Looks like it. We can even double check with the graph. Perfect. Okay. So if you have any questions about any of this, please let me know.